But we actually have 2 speakers. It's a 2-for-1 talk, okay? So we get 2 fun facts. The first, well, not the first. One of them, as a baby, Tom Cruise once rubbed his head for good luck. Apparently this is his words. Apparently being a ginger has some perks. And it seemed to work out for Tom too. And then speaker number 2, when he's not building models, he's training for the 2025 Chicago Marathon on October 12th. He believes long distance running and deep learning have more in common than you'd think. Pacing, patience, and learning from every step. Please welcome Jon and Vincent.
Glad you went with that choice. Just quick introduction to who we are. I'm Jon Sege. I'm the AVP of our data management and analytics department at White Plains Hospital, which is a hospital a little bit north of the city here. Many of you may know it from Metro North. And by the way, our sort of nickname or acronym is DNA. That's where the song comes from. My background is in environmental engineering. I've been working in the healthcare space for about 10 years now. And I apologize for my voice. I'm actually a little bit sick at the moment, ironically. So I'm going to ask Vincent, please introduce yourself as well.
Hi, everyone. My name is Vincent. I'm a data scientist working at White Plains Hospital. My past experience including financial, reinsurance, private equity, and recently I just switched to healthcare. And I'm passionate about using data for good.
So coming off of Swatik's super interesting, very high-level talk, we're going to zoom in quite a bit here to talk a little bit about our team, what we do within a healthcare space, which I think is very typical of what a lot of teams like ours do within hospitals. And to start with that, I'll just give you a picture of what we do and who our stakeholders are. So like many other organizations and hospitals, we have sort of a more distributed data team that does things like BI, so reporting on KPIs and how are we doing and quarterly metrics and so on. We sit within that structure to try to develop the pipeline from what to why to what next, meaning not just what happened, but why did that happen, and can we start to give you predictive outcomes on what might happen next. And really who we work with the most is the highest levels of the hospital, executive leadership, all the way down to the folks, clinical leaders and clinicians themselves who are in the charts every day trying to make decisions on what to do to provide the best possible quality of care for the patient at the bedside where they are. So in many ways, our team for years has sort of been a learn and churn team is what I like to call it, which basically means you get a use case from a stakeholder, you think about all the possible data sets and features you might need to use, and you figure out, you create a new Jupyter notebook, you start bringing in data sets, you spend a couple of weeks maybe engineering some features, you train a model, sklearn or PyTorch or whatever else, you churn it out and you move on. So what's difficult in a hospital setting, healthcare in general, are a couple of things, and I want to highlight these first to give you an idea why we've started to think about moving away from that sort of ad hoc, bespoke machine learning approach towards using deep learning models that encapsulate some of the key features that we use over and over again. So the issues are these. Number one, feature density here. So on the left side is an actual plot showing one of our feature matrices that we use very commonly in our different models. So the red dots are the points where there is a known value for that feature, and the white spots are where there are no known values. So I don't know if you can even see any red spots on there, but these matrices are extremely sparse. So we may have many instances, for example, this thing, diagnosis codes, there's many thousands of them that you could have, but most people don't. So we end up with these very sparse matrices. And number two is that these features are all very highly related to each other in many cases. If you have a certain diagnosis, you're going to get a certain procedure, you're going to get a certain medication, and we want to be able to capture those things without having to learn it every time. So I want to take you down to the ground to a use case that we came up with last year that we sort of started working with one of these deep learning models on, and then I'm going to have that segue into Vincent to tell you the more interesting part, which is what we did. So what we're aiming for here is to be able to give our clinicians an idea of, are we connecting our patients with the proper specialist at the right time, right? So if you go to the hospital, maybe you go there because you tripped and fell, but actually, you may have other things going on, and really it'd be very important for you to talk to somebody to look at your heart, somebody to look at your lungs, whatever. There may be people involved who are not the reason you are there, but it's very important that you talk to them. Now, quite often, hospitals are busy places. You can't think about everything in holistic terms all the time. So we may miss those connections, and so we built a model to help support our clinicians in understanding what those needs were. So here's obviously redacted view of what this model turned into, and a very clear use case of why it's important. So we had a patient come in for sepsis, which is a blood infection, for those who don't know. Totally not related to the heart necessarily. We took a model that you're about to hear about how we trained it, and ran this particular case through that model. The model said you should really have this person talk to a cardiologist, heart doctor. So, this is retrospective. This model wasn't live at the time, this historical case, but the person was never connected with a cardiologist. And then, unfortunately, 24 days later, they came back with a heart attack. So, no fault of the doctor or the clinicians or ours. The person came for something else. It wasn't top of mind. But models like these can help surface things that may not be the primary reason for the visit and prevent this type of case in the future. And I am going to hand it off to Vincent to tell you a lot more about what we did to get there.
Thank you, John. So next I'm going to explain why we use the LSTM model for this prediction. So it's a multi-label, we are predicting a medical specialty, which is a multi-label task. So LSTM supports multi-label output. And the input of the model is the list of the SD10 code with different lengths for each widget. So LSTM can handle different lengths of input, and also the input, their order, and order matters. So the model can, the LSTM can model the long-term dependency of this code. And lastly, LSTM has a special mechanism called memory cell. The diagram on the right is one memory cell. Basically, it contains 3 gates to control how information flowed. And here is how each gate works. The forget gate decides what information to keep. The input gate decides what new information to add. And together, they updating the cell's long-term memory. And the output gate using this memory to decide what information to pass forward to for the next prediction. So on the left is the input, the sample input and output data. The input is a list of the SD10 code, and the output is a list of the specialties. To evaluate the model, we use a Jacob index, which measures the overlap between the predicted value set and the actual value set. So the score of 1 means completely overlap, and the score of 0 means no overlap at all. So for the multi-label task with 82 distinct values, the training score of 0.65 and validation score of 0.64 means the model has shown generalization without overfitting issues. So after building this model, we started thinking about to build a model that can capture the summary of the widget. That led us to the idea of embedding, which will compress thousands of the clinical code into a dense vector representation, and it will allow transfer learning and also reduce overfitting. So the first model, the first version of the embedding that we use is called mathematical modeling. The idea was inspired by Troy and Devlin's work. So we combined the idea to build a graph convolutional transformer on a clinical node. So it functions like a BERT on EHR data. So the key insight is EHR data is more than a list of the clinical codes. It has an underlying graph structure where the diagnosis, procedures, and treatments, they are interconnected. And then we train a model using Graph Convolutional Transformer to learn the hidden relationship among these elements. So here is the how we can represent a widget as a graph. So for each widget, it contains several components. The SD10 diagnosis code in the first layer, the CPT procedure code in the second layer, and there are some other features such as medication, naps, and imaging at the bottom of the layer. And the widget also ordered by time for the same patient, allowing the model to capture how past widgets will influence the future ones. So here is the two key components of Graph Convolutional Transformer. The Graph Convolutional network on the left, then the node to learn from its immediate neighbors, and the transformer component on the right uses the attention to allow the ask the node to learn from its most relevant node, even if they are far away. So by combining these two components, the GCT it combines both local and global context. Here is the full pipeline of the MCM model. So the idea is simple. For each inpatient widget, we randomly mask some of the SD10 code and CPT code, and then we train a model to predict the mask code from the remaining context. We train a model for over 375,000 iterations, and then we check the performance every 6,000 steps. The evaluation metric we use for this task is mean reciprocal rank and top one accuracy. The best model achieve MRR of 0.43 and top one accuracy of 32.7%. So which means about a third of the time, the model predicts the correct code with the first guess. Now considering there are over 13,000 features, so if for random guessing, the top one accuracy will be 0.0077%. So which means the performance of this model is solid. So now to validate whether the embedding generated by mask code modeling carries meaningful clinical information, we are comparing the performance with the one-hot encoding based as the baseline model on two downstream tasks. The first one is readmission and then length of stay. We can see here for both tasks, the MCM embedding underperform compared to the one-hot baseline model. So the validation is a kind of disappointing. The reason for that is because the model, the embedding generated from the mask code modeling is not good at capturing, it's not good at predicting the clinical outcome because it lack of the widget level supervision, so it misses the clinical context of the widget. So in order to make the embedding to be more representative of the widgets, we have to add some widget level tasks. Then let us to develop the MES model. So a MES is a multi-task learning that runs 6 tasks at the same time. It is designed to balance the tasks, so no one single task dominates the learning. The key challenge for the multi-task learning is how to balance the loss with different loss scale. Simply summing all the loss with equal weight will allow the loss with higher magnitude to dominate the learning, which will bias the model. The homostaticity uncertainty weight addresses this by downweighting a task with higher uncertainty and balance the loss scale. However, it still suffers from gradient conflict and the loss explosion. So the final solution we use is to integrate gradient normalization with the HUW. So HUW statically balance the loss scale using the uncertainty weight. The grad norm dynamically adjusts the gradient magnitude to make sure all the tasks are learning at the same pace. And we also introduced a KO divergent regularization to smooth the attention distribution, which will improve the generalization and reduce the overfitting. So here is the gradient conflict I mentioned earlier for using the HUW only. We can see that some tasks are going down, but then others are bouncing up and down, which is a clear sign of gradient conflict. By adding the grad norm, all task loss are going down. And here is the loss explosion for using the HUW only. We can see at the top, we can see the emission loss and mortality loss both up in the late training stage, which caused the total loss to explode. By adding the grad norm, stabilize the loss. And the total loss follow the U-shaped pattern, primarily driven by the noise from the emission loss and the ESI loss. So these two tasks are difficult to predict using the diagnosis code only. So in future model version, we think about replacing these two tasks. And here is how the model reconstruct the graph for each widget. On the left is the attention from the widget embedding. The longest bar represents the most important diagnosis code for these widgets. And then we trace the attention for this key code to other related CPD code. So it started with a prior, which is a conditional probability, and then it's progressively refined throughout the self-attention blocks. Again, we are also validating a mass embedding against the MCM embedding and the one-half baseline model. So for re-emission, the mass embedding outperform the MCM embedding, also outperform the one-half embedding, one-half baseline. And for length of day, the MS embedding outperform the MCM embedding, but slightly underperform the one-half baseline model. For ESI tasks and mortality tasks, the MS embedding achieves similar performance with the one-half embedding, one-half baseline. And for disposition, this is a task was not included in the MS multi-learning task. So the embedding achieved comparable performance with the one-half baseline model. So this is a strong evidence that the embedding has effective transfer learning on unseen tasks. And also the validation proved that the embedding generated by a MS model, it has successfully learned and contained the meaningful clinical information from the widget. And clustering also works better with embedding. So on the upper left corner is the clustering on the one-half features. So as we can see, these clusters are heavily overlapped, and the Hugh score is negative, meaning the data is noise because of the high dimensionality. And the clustering on the embedding produces distinct clusters. And on the right is the summary for the clustering on embeddings based on the top 10 ICD-10 code. From the summary, you can see these clusters follow a clear clinical pattern. Summarize, the embedding can be used as a powerful foundation model. It distills thousands of features into a dense vector representation. It allows transfer learning while reducing the overfitting and simplifying the deployment. As for the next step, we are focused on both the deployment and the enhancement. For deployment, we are working on deploying an embedding model to a vector database for easy downstream reuse. And then for enhancement, we will add new features to the graph, such as medication as the third layer of the graph. We are also expand the data coverage to include sibling hospitals data. And we are going to revise the task set. So we are confident after these steps, the embedding can be the true universal representation of the widget. So with that being said, thank you so much for your attention. And if you have any questions, feel free to reach out either John or me. Thanks.